Welcome to your go-to educational hub on YouTube. Here, we dive deep into big data topics, unravel complex concepts, and share knowledge that empowers and enlightens. Whether you're a lifelong learner, a curious explorer, or a student seeking clarity, you've found the right place. Subscribe and join our community of thinkers, dreamers, and doers. Let's learn and grow together. Oh, what is big data? History of data management, evolution of big data. Oh, why big data? Big data refers to extremely large and complex datasets that cannot be effectively processed using traditional data processing applications. These datasets typically consist of structured, semi-structured, and unstructured data from various sources such as social media, sensors, mobile devices, and more. Big data is characterized by what is often referred to as the 3 V's: volume, velocity, and variety. Volume. Big data involves large volumes of data. Traditional database systems may struggle to handle the sheer amount of data generated and stored. Velocity. Big data often arrives rapidly and needs to be processed quickly. This includes real-time data streams from sources like social media, sensors, and transactional systems. Variety. Big data comes in various formats, including structured data, example, relational databases, semi-structured data, for example, XML, JSON, and unstructured data, e.g., text, images, videos. Managing and analyzing this diverse range of data types can be challenging. In addition to the 3 V's, 2 more V's are sometimes added to characterize big data: variability and veracity. Variability. Big data can exhibit inconsistencies and variations in its structure and meaning over time. Veracity. Big data may include noisy, incomplete, or inconsistent data. Ensuring data quality and reliability is crucial for effective analysis and decision-making. To effectively harness the insights from big data, organizations often employ advanced analytics techniques such as data mining, machine learning, and predictive analytics. Technologies like distributed computing, NoSQL databases, and cloud computing are commonly used to store, process, and analyze big data efficiently.
Evolution of big data.
The history of data management and the evolution of big data can be traced through several key milestones. Pre-computer era. Data management primarily involved manual methods such as ledgers, file cabinets, and physical records. Datasets were relatively small, and analysis was limited by manual processing capabilities. Mainframe era, 1950s to 1970s. Mainframe computers introduced centralized data storage and processing. Databases were developed to organize and manage structured data efficiently. Technologies like hierarchical databases, e.g., IBM's IMS, and network databases, e.g., colossal, emerged. Relational database era, 1970s to 2000s. Edgar F. Codd's relational model laid the foundation for modern relational databases. Relational database management systems, RDBMS, like Oracle, IBM DB2, and Microsoft SQL Server became prevalent. Structured query language, SQL, standardized database querying. Data warehouses were introduced to store and analyze large volumes of structured data for business intelligence. Internet era, 1990s to 2000s. The growth of the internet led to an explosion of unstructured data, text, images, videos, generated by websites, social media, and other online sources. Search engines like Google pioneered large-scale data indexing and retrieval techniques. Technologies such as XML and JSON facilitated the exchange of structured data over the web. Big data era, 2000s present. The term big data gained prominence to describe datasets too large or complex for traditional database systems to handle. Technologies like Hadoop, developed by Doug Cutting and Mike Caffarella, introduced distributed storage and processing of big data using commodity hardware. NoSQL databases emerged to handle unstructured and semi-structured data efficiently, offering scalability and flexibility. Cloud computing platforms like Amazon Web Services, AWS, Microsoft Azure, and Google Cloud Platform, GCP, provided scalable infrastructure for big data processing and storage. Frameworks like Apache Spark offered faster and more versatile big data processing capabilities compared to MapReduce. Advanced analytics techniques, including machine learning and artificial intelligence, became integral for extracting insights from large datasets. Real-time data processing technologies like Apache Kafka enabled the handling of streaming data for instant insights and decision-making. Current trends and future directions. The proliferation of Internet of Things, IoT devices, is generating massive amounts of data, requiring scalable solutions for storage, processing, and analysis. Edge computing is gaining importance for processing data closer to its source, reducing latency and bandwidth usage. Data governance and privacy regulations are becoming increasingly important as concerns about data security and privacy grow. Hybrid and multi-cloud architectures are being adopted to leverage the strengths of different cloud providers while mitigating vendor lock-in risks. Continual advancements in hardware, e.g., GPUs, TPUs, and software technologies are driving further innovations in big data management and analytics. Fishing has evolved significantly since the 16th century, with boats capable of going to sea transforming the industry. Traditional methods involved compass, sextant, and inside knowledge. By the late 19th century, fishing had become commercialized with trawlers and onboard processing capabilities. Technological advancements have transformed fishing from an art to a science, with modern boats using high-tech navigation systems and GPS. Fishermen now know where fish are, when to cast nets, and when to cast nets for the best catch. Why big data? Big data came into the picture due to several interrelated factors, each contributing to the need for new approaches to manage, process, and extract value from large and complex datasets. Here are some key reasons why big data became prominent. Exponential data growth. With the proliferation of digital technologies, data generation has grown exponentially. This includes data from sources such as social media, sensors, mobile devices, and internet-connected devices. Traditional data management systems were not equipped to handle the sheer volume, velocity, and variety of data being generated. Advancements in data storage. The increasing availability of affordable storage technologies, coupled with declining storage costs, made it feasible to store vast amounts of data economically. Organizations sought ways to leverage this data for insights and competitive advantage. Technological innovations. Advances in distributed computing, parallel processing, and cloud computing technologies provided the infrastructure needed to store, process, and analyze large datasets across clusters of commodity hardware. Technologies like Hadoop, Apache Spark, and NoSQL databases emerged to address the scalability and performance requirements of big data analytics. Web and social media. The rise of the internet and social media platforms led to the generation of massive amounts of unstructured and semi-structured data. Organizations recognized the potential value of this data for understanding customer behavior, market trends, and sentiment analysis, driving the need for big data analytics. Business needs. Organizations across various industries recognized the importance of data-driven decision-making. To gain competitive advantage, improve operational efficiency, and enhance customer experiences. Big data analytics offered the promise of extracting actionable insights from large datasets to inform strategic decisions and drive business growth. Scientific and research challenges. Scientific research in fields such as astronomy, genomics, climate science, and particle physics generated enormous datasets that posed significant challenges in terms of storage, processing, and analysis. Big data technologies emerged to address these challenges and enable breakthrough discoveries. Regulatory and compliance requirements. Regulatory requirements, such as data retention policies, privacy regulations. Example, GDPR and industry-specific compliance standards necessitated the need for robust data management practices. Big data technologies offered capabilities for data governance, security, and compliance. In summary, the emergence of big data was driven by a combination of factors, including exponential data growth, technological innovations, evolving business needs, and scientific challenges. Big data analytics has since become an essential capability for organizations seeking to harness the power of data to drive innovation, make informed decisions, and achieve competitive advantage. Elements of big data will be discussed in the next video. Until then, stay tuned for more updates. Please do like, share, and subscribe at Edspirational-techies, technology for everyone and everywhere.